Hello, ladies and gentlemen, and welcome to the Triune Physics, aka Physics Bible. Today, we'll be dealing with collision. Is that clear? Part of linear momentum and conservation of linear momentum. By definition, collision occurs when two or more objects come in contact with each other, exerting a force or forces on one another. Are we here? For a relatively short period of time. You understand this concept if you consider the concept of accident, or when two cars hit each other, or when two objects collide with each other. Are we here? So collisions can involve physical contact, like two cars hitting each other, or two balls hitting each other, or by interaction at a distance. For example, charged particles repelling each other at a distance apart. Are we together, please? So when you consider collision, you consider accident. What are the most important components in this definition? We have two or more objects, as you are seeing being displayed on your screen. Ball 1 and ball 2 of mass 1 and mass 2. Okay, then what happens to them? They exert forces on each other. Are we here? They exert forces on one another. Then there has to be a contact. If you are considering contact now, there has to be physical contact before there can be a change in direction. And then you can see relatively short period of time. Yes, it happens all of a sudden. Consider an accident. You understand this concept vividly. So, if you observe this, for example, you see these two cars hitting each other. You see there is an interaction if you consider magnets. Are we here? Interaction, magnets, charges, then physical contact, cars, balls hitting each other. Is that clear? Alright, let's consider these example by using this diagram. If these are two balls, ball 1 of mass 1 and ball 2 of mass 2, are we here? You can see there will be a collision between these two objects. Now, if this object moves in this direction, this one in the other direction, that is 0 in the other direction, opposite direction to 1, this has to do with contact now. Is that clear? They have to hit each other before these balls can change their direction. What about if you consider a magnet, for example, north and north pole? What happened to them? There's going to be a repulsion. Is that clear? Hence, there is no contact, but there is a force being exerted. I hope you can get this part. So, there is an interaction because they are both within the magnetic field. So, physical contact for the balls and non-contact for the magnet. So, what are the types of collision? Number 1, we have elastic collision. Number 2, we have inelastic collision. And number 3, we have perfectly inelastic collision. Please note that some textbook can capture number 3 and number 2 together as one. Is that clear? So let's pick the first one, elastic collision. In elastic collision, it is a collision, okay, where both the momentum, okay, and the kinetic energy are conserved. You can use the word preserved. Are we here? For example, if we have the collision of billiard balls, that is snooker balls, or the collision of molecules in motion, of course, you know they will be randomly placed. And then number 3, we have a tennis ball that bounces back to its original height after hitting a hard surface. So all these are just simple examples of elastic collision. Are we together? Now, if we proceed further, you realize that this collision has its own characteristics. Number one, we have the total kinetic energy before the collision will equal the total kinetic energy after the collision. That's number one. When you deal with kinetic energy, before, after, very important. Are we here? Then number two, total momentum before the collision will equal total momentum after the collision. Take note of before and after. Is that clear? And take note of momentum. Then kinetic energy. Please take note of these. Energy is conserved. Is that clear? Now, if we derive a formula, we want to derive a formula now, so that you can use that to solve your mathematical problems. Number one, we have momentum conservation. Momentum conservation. We have m1 u1 for the first body plus m2 u2 will equal m1 v1 plus m2 v2 if these involve only two bodies, which is m1 and m2. Then for kinetic energy conservation, we have, of course, you know that under kinetic energy, recall that kinetic energy is equal to half mv squared. Are we here? But if you consider the mv in this equation, you realize that it's giving us momentum. Is that clear? So that means if you square this, you can obtain momentum inside kinetic energy. I hope you are getting this part. So mv denotes final momentum. Yes, recall. So hence, if we substitute that, then we'll have what? Kinetic energy conservation. Okay? We equal 1 over 2 m1 u1 squared. Okay? Because we are dealing with energy, plus 1 over 2 m2 u2 squared will equal 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared. I hope this is clear. Take note of this equation. It's very, very important. Where our m1, m2 will equal the masses. Is that clear? Of the objects. Of course, very important. And then u1, u2 will equal the initial velocities of the masses m1 and m2. Is that clear? Then v1, v2 will equal the final velocities of the objects, which is m1 and m2. Is that clear? So please take note of this equation. It's very important. Yes, it's very important. We are highlighting it so that you take note of this. Please recall that energy is conserved here. So we have two main equations that you can use here. Then number two, we have the inelastic collision. Number two and number three are connected, please. It is a collision where momentum, underline that momentum, is conserved, but kinetic energy is not conserved. Do you understand this part? Momentum, kinetic energy, conserved. These three things. Kinetic energy is not conserved. Momentum is conserved. Please take note of this. All right? Now, if we proceed further, you realize that, for example, a car crash, are we here? Where the cars deform. If you observe that, that is an example of inelastic collision. Is that clear? Momentum is not conserved. Please observe this image. Okay, if, for example, this M1 car 1 hits car 2 by crashing it, it will deform, or both might even deform in shape. Hence, what will happen? Characteristics. Number one, total momentum before collision will equal total momentum after the collision. Are we here? Then number 2, you realize that kinetic energy is lost, meaning converted into other forms of energy, such as heat or sound, which is why you hear loud boom when there is an accident. Part of the energy has been converted into that sound you hear. Is that clear? So, before, after, converted from what? Heat. Converted into heat, rather, or sound energy. Please take note of this. Okay? Alright, let's proceed further. Please note that the colliding bodies, okay, stick together and move as one unit after collision. That is, their velocities are the same after collision. So if that is the case, then V1 will equal V2 and is equal to V3, which is equal to V if you have up to 3 objects. Now observe these two balls, M1 and M2. M1 has initial velocity. M2 doesn't have initial velocity. Now watch, as M1 hits M2, what happens? M2 begins to move with the velocity of M1, which gives us the final velocity, and they are the same. So V1 is equal to V2 and is equal to V. Are we together? But for M1, U is active, while for M2, U, which is initial velocity, is inactive. So M1, U1 plus M2, U2, that is for conservation of linear momentum, will equal M1, V1 plus M2, V2. Are we together? Okay? So if we proceed further, you realize that by substitution, that V1 is equal to V2 and is equal to V. Please take note of this. Then let's substitute proper, becomes M1U1 plus M2U2 will equal M1V plus M2V. So V is common between M1 and M2 when you consider the final velocities. Are we here? Now, if you observe for the initial velocity, okay, M1U1 plus M2U2 will equal what? V into M1 plus M2. I hope you are getting this part, because V is common between M1 and M2 when you consider the final velocity. Please take note of this equation, very important for you. Now, where V is equal to what? The common velocity between M1 and M2 when you consider the final velocity, please. The common final velocity. Okay? Now, if M2 is static, you've seen it above when I made reference to that. If it is stationary, that means no initial velocity, then M2 will have U to be 0. I hope this is clear, please. U becomes 0 for M2. So U2 is equal to 0. Okay? So we are going to substitute that into the equation above. Okay? Substituting into the equation above, we have M1U1 plus M2 into 0. Okay? Is equal to V into M1 plus M2. Close your bracket. Is that clear? M2 multiplied by 0 is 0. Okay? So all we have left to be M1U1 plus 0 is equal to V into M1 plus M2. Is that clear? Now we want to make V the subject of the formula. So M1U1 is equal to V into M1 plus M2. So let's divide through by M1 plus M2. Is that clear? So that we can make V the subject of the formula. Hope this is clear to you. Then M1U1 will equal V into M1 plus M2. Divide through by M1 plus M2. M1 plus M2. Okay, so that this cancels this. So V is equal to V V is equal to M1 U1 divided by M1 plus M2. I hope this is clear. This is an important equation also if you are asked to calculate for final velocity. Is that clear? So take note of this equation. It is very important. Now, how about if you are asked to calculate the kinetic energy of the system? The kinetic energy of the system. Recall that kinetic energy is half mv squared. So we'll bring that idea into this. Are we together? So the initial kinetic energy will be represented with KE1, okay, before collision, which is U. That's what differentiates that. So we have KE1 is equal to, what are we going to have? 1 over 2 M1 U1 squared plus 1 over 2 M2 U2 squared. Okay? Now, the second part, if the final kinetic energy is denoted by KE2, which is after collision. Okay? After collision, of course, V will come in now. Hence, we have KE2 will equal 1 over 2 M1 V1 squared plus 1 over 2 M2 V2 squared. Is that clear? Now, if you observe from the equation above, we said that V1 and V2 are the same. So if that is the case, then we can now say boldly that V1 is equal to V2 and is equal to V. So let's substitute. KE2 will equal 1 over 2 M1 V squared plus 1 over 2 M2 V squared. I hope you are getting this part. So let's reduce this by factorization. So we have KE2 will equal 1 over 2 into M1, okay, plus M2 into V squared. You close your bracket. So V squared multiplies whatever is inside the bracket. Now, since KE1 is greater than KE2, the reason is because it is M1 that has the initial velocity. And once they collide, the velocity begins to die down. Is that clear? So, and it will now depict loss in kinetic energy. So loss in kinetic energy is equal to KE1 minus KE2. Is that clear? Because KE1 is greater than KE2. So now KE1 is equal to 1 over 2 into M1 U1 squared plus M2 U2 squared. Close your bracket. Then we know that KE2 is equal to 1 over 2 into M1 plus M2 into V squared. Are you here? Now, if we proceed further, let's proceed further. If KE1 divides KE2, okay, initial divides final, then KE1 divides KE2 and is equal to 1 over 2, okay, to now equal 1 over 2 into M1 U1 squared plus M2 U2 squared. M2 U2 squared. Is that clear? Close your bracket. All divided by, okay, 1 over 2 into M1 plus M2, close your bracket, V squared. I hope this is clear. Now, we can divide through, isn't it, by 1 over 2. Is that clear? So if we divide through by 1 over 2, what are we going to have? So cancel 1 over 2. 1 over 2 cancels out 1 over 2. So KE1 divided by KE2 will equal M1, right here, M1 U1 squared plus M2 U2 squared, all divided by all divided by v squared into m1 plus m2, close your bracket. Exactly. So take note of this. So if m2 is static, recall that u2 will become 0, isn't it? Because m2 doesn't have initial velocity. So with that being said, we need to substitute that into the equation above. Is that clear? So we're going to substitute u2 to be 0 into the equation above. Okay? Then ke1 divided by ke2 will equal m1 u1 squared plus m2 into 0, which becomes 0, divided by m1 plus m2 multiplied by v squared. I hope this is clear. So finally, what we'll be having left will become what? ke1 over ke2 will become m1 u1 squared, all divided by, open bracket, m1 plus m2 close bracket, multiplied by v squared. Is that clear? This gives us our final equation. If you consider this equation or compare with the previous one, the differences between the momentum and the kinetic is the square. Are you here? It's just the square. Check the two, you're going to see that. So please, that is that for these. Number 3. Number 3 is part of number 2. Some textbook might not separate them. So perfectly inelastic collision. Under this, it is a special case of what? Inelastic collision. Which is why most of the things we've done above will be captured here too. So, a special case of inelastic collision where the objects stick together after the collision. We've done that mathematically. You've seen that. Is that clear? Would give us V1 is equal to V2. Is that clear? And is equal to V. So if two clay balls, for example, collide together, what happen to them? They might stick together. So this gives you an example of perfectly inelastic collision. What are the characteristics as seen above? Number 1, maximum loss of kinetic energy. Okay, to either sound or heat. Number 2, objects move together. Okay, with a common velocity after collision. Is that clear? After collision, we've done that mathematically. Please refer to the formulas above, please. So, generally, our formula, momentum conservation. Are we here? m1 u1 plus m2 u2 will equal v into m1 plus m2. Is that clear? Take note of this, where v is equal to the common velocity. Is that clear? After collision, please take note, after collision. Then we have captured that above. Okay, take note. All right, let's proceed further as we begin to round off this class. Key concepts or key formulas under collision. Are you here? Let's summarize whatever we've done today. Now let's begin quickly. Number 1, we have momentum conservation. Okay, momentum conservation, which is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Take note of this, very important. Now let's proceed. Number 2, kinetic energy conservation. Kinetic energy conservation, okay, which is elastic collision. For elastic collision, we have 1 over 2 m1 u1 squared plus 1 over 2 m2 u2 squared will equal 1 over 2 m1 v1 squared plus 1 over 2 plus 1 over 2 m2 v2 squared. Okay, take note of these also, very important. Is that clear? Now note, this applies only to elastic collision. Take note of this, please. Okay, this applies only to elastic collision, and for momentum conservation it applies to all types of collision. Okay, so momentum conservation is a general equation for collision. Number 3, coefficient of restitution, E. Let's represent that. E will equal v2 minus v1 all divided by u1 minus u2, final velocity against initial velocity. So if E is equal to 1, it becomes perfect elastic collision. Is that clear? Then if E is greater than 0 but less than 1, it becomes partially, okay, inelastic collision. Are we here? Then if coefficient of restitution is equal to 0, it becomes perfectly inelastic collision. I hope this is clear. So with this, summarily, using a table to represent some key concepts, okay, summary table, let's write this quickly. Okay, if we have, let's write this, types of collision, then momentum conservation or conserved, kinetic energy conservation or conserved, objects stick together. If objects stick together, then we're going to have, for number one, for elastic materials or elastic collision, inelastic collision, and perfectly inelastic collision. What happened to momentum conserved? Yes. Inelastic? Yes. Perfectly inelastic? Yes. Then kinetic energy conserved? Yes. For inelastic and perfectly inelastic, no and no. Then objects stick together? No, no, yes. I hope this is clear. Connect to our social media handles at Physics Bible, the Triune Physics, for latest update. Thanks for joining us. Stay equipped, stay liquid.